So, welcome to the Quantum BV colloquium of today. I'm João Bravo, and today with the quantum team at Prof. I'll guide you through the colloquium. So, since last year, Quantum BV is the state initiative for quantum activities in Baden-Württemberg to pool all these competencies, so quantum competencies, and to create an overarching umbrella over these competencies and to further strengthen these networks and make them more visible. So with this colloquium, we want to further promote the scientific exchange on quantum hardware and also algorithmic topics in the field of quantum computing and related, and to present the latest developments in this research area and to promote the idea of co-development of quantum solutions. So today I have the honor of introducing Professor Achim Kempf from the University of Waterloo. So Professor Achim Kempf's field of research is physics of information and AI. So he's based in the University of Waterloo, as I said, near Toronto, Canada, where he's also an associate member at the Institute of Quantum Computing, Institute for Quantum Computing, and the Perimeter Institute. He has held the Canada Research Chair in the Physics of Information at the University of Waterloo, and he has chaired the International Society for Relativistic Quantum Information. So previously, he was a research fellow at Cambridge University, and he has also studied here at the universities of Heidelberg, Karlsruhe, and Munich. So the title of the talk is The Dynamics of Entanglement in Adiabatic Quantum Computing. And in this talk, Professor Kempf will address the question about the level of difficulty of the problem of combinatorial optimization translates into the hardness of the corresponding adiabatic quantum computation by analyzing the adiabatic dynamics of entanglement. So you can also online post questions in the chat as always. And with this, I hand it over to you.
Thank you, João. Happy to be here. Thanks for the kind invitation. I'm going to present work with Barbara Schroeder and Aina Gabasov, hopefully also online at the moment. So the core question I want to address in this presentation is the question of how the hardness of a mathematical problem translates into the physical implementations of this calculation speed. So we would expect that the harder a mathematical problem is, the longer it takes to carry out the calculation on a machine. And this question is important to understand in detail because only then can we hope to understand what makes a quantum advantage. Now, there are different ways to address that question of what makes a quantum advantage and how does the mathematical difficulty of a problem translates into the physical difficulty of performing the calculation. And the framework that I will use in this presentation is that of adiabatic quantum computation. And this work that I will talk about today has been made possible because of new non-perturbative mathematical tools. So I will start the presentation going through those mathematical tools in isolation. So before we even go into the physics, let's just look at the mathematical tricks that we bring new to the table and that enable us to say something new about the relationship between mathematical hardness and physical hardness. So there are going to be three mathematical tools that I talk about, and this is the first one. All three of them have to do with what might be called rank 1 perturbations. So let's say we start with a self-adjoint matrix, typically Hamiltonian. Let's call it H naught. It has a spectrum of eigenvalues En, and it has eigenvectors psi n. And then we perturb it. We perturb it by adding to this Hamiltonian a projector. So V is some normalized vector in the Hilbert space, and we add a multiple of that projector. Projectors are self-adjoint, so the whole thing is self-adjoint. So this Hamiltonian, or this self-adjoint matrix, is a self-adjoint matrix that's parameterized by a parameter mu. what has been known is that you can calculate exactly an equation that the eigenvalues and this parameter mu obey. It's this secular equation. See, there are the eigenvalues of the original matrix, H0, and here the lambdas are the eigenvalues of H of mu. So the mu's are the lambdas are functions of mu. This equation allows you to express mu as a function of lambda. But what we really want is the opposite. We want the eigenvalues as a function of mu. It should not be possible to calculate them because, you know, if you want to write that as a polynomial whose roots you want to find, the characteristic polynomial of that Hamiltonian there or that self-adjoint matrix there, it generally has a degree larger than 5 because we are dealing with high-dimensional Hilbert spaces here. And then by Galois theory, there shouldn't be an exact expression in terms of radicals that tells you what these eigenvalues are. But what's new is that we found a way around that. We can actually tell what the eigenvalues are non-perturbatively as a function of the mu. And the way to do that is to express mu as a function of lambda. We have that. We can just solve that equation quite easily for mu. And then do the Taylor expansion of that. We know that it's convergent and all that. And then we do an inversion of that expansion using Lagrange inversion and show that we again get convergence. And this goes around the constraint of Galois theory because that's not an expression in terms of radicals. Instead, it's a power series. So that's possible, and it was a hell of a job to do this inversion, and it's generating an enormous number of terms, but magically they collapse into a reasonable series at the end that one can actually work with. And so fundamentally it's Galois theory that we are circumventing, but the exact theorem, of course, is Abernoulli's theorem about not being able to calculate the roots of the characteristic polynomial when the degree is too high. So the first tool is that we can actually calculate for any such Hamiltonian, we can now calculate exactly what the eigenvalues and what the eigenvectors are with all terms known. So it's not like we have an expansion and in order to calculate the 21st coefficient, we have to calculate the first 20. No, we have exact expressions for all orders directly. It's not an induction. Second mathematical tool is that we understand now better what happens when levels cross or don't cross. If you have a Hamiltonian like this one, a self-adjoint matrix like this one is parameterized, then clearly as this parameter mu changes, this operator changes, and therefore its eigenvalues change and its eigenvectors change. And if we think of what the eigenvalues do, we can view this as, the eigenvalues we can draw as a function of this parameter mu, this coupling parameter mu, and so the eigenvalues go something like this. And they don't go in parallel, they could in principle cross. When you have a time-dependent Hamiltonian, the eigenvalues could do whatever, and so they might also cross. But it's been known for about 100 years that in practice they never cross. As you have a time-dependent or parameter-dependent Hamiltonian, the eigenvalues never cross. They can only cross if there's a symmetry enforcing it. Generically, they can never cross. So eigenvalues can, as mu grows, the two eigenvalues can get very close, but eventually they have to separate and they cannot cross, unless if there's an exact symmetry enforcing the crossing. So it's been known that there is this level repulsion phenomenon, avoided level crossings, and it has implications in physical chemistry and really all over the place. Now, what's also been known, but now we can calculate this non-perturbatively, is that when two eigenvalues narrowly avoid crossing during the evolution of a Hamiltonian, then they swap eigenvectors. It's not so weird if you think about it, because if the two eigenvalues were actually crossing, right, then clearly the lower eigenvalue comes along with its eigenvector and then keeps having its eigenvector, right? So it would look as if they swap. But if they narrowly avoid crossing, then too, you have that during the narrow avoidance, the two eigenvalues that narrowly avoid crossing will swap their eigenvectors. Not perfectly, but very perfectly if the avoided level crossing is very closely avoided. The further away, the bigger the gap is that is between the two eigenvalues as they approach, the bigger the gap is, the less perfect will be the swapping of the eigenvectors. And if the crossing is very narrowly avoided, then they almost perfectly swap the eigenvector. And now we can calculate all of those things non-perturbative. For later purposes, adiabatic quantum computing and quantum computing in general, it will be very important to remember that the narrower the gap, the more complete is the swap of the eigenvector. And we have exact expressions that relate the gap size to the amount of eigenvector exchange. And that was the second mathematical tool. And the third mathematical tool is an asymptotic property that in hindsight is kind of obvious, but it needs to be pointed out. It's very important. Consider the limit from mu going to infinity. Let me just remind you. Here's our equation, Hamiltonian as a function of mu. And so we have the original Hamiltonian, we add a multiple for projector, where v is some arbitrary generic normalized vector. And now let's assume we let mu grow larger and larger. What will happen? Well, initially, for mu being 0 or some small finite value, having this v, a generic v, means that v is not an eigenvector of the H of mu. Why would it be? It's just, generically it's not, it's a generic vector. But imagine you crank up the mu, then this part will dominate over that. And eventually, from mu going to infinity, what you will find is that v becomes effectively an eigenvector of H of mu. The larger the mu is, the more exactly it is true that v becomes an eigenvector of H of mu. Just think of it. So this is a matrix, and then you add these entries there, and they're just way bigger than anything else. So we have the exact formula, so we can prove this, but intuitively it's also quite obvious that v becomes an eigenvector of H of mu if mu goes to infinity. But that has another important consequence, which is that in the limit from mu going to infinity, as v becomes approximately an eigenvector to H of mu, in fact it becomes exactly an eigenvector in the limit, we also have that the other eigenvectors of H of mu, all of the other eigenvectors must therefore become orthogonal to v, right? Because if v is an eigenvector, well, the eigenvectors of the self-adjoint operator are orthogonal to each other. So all of the eigenvectors become orthogonal to this vector v if we crank up the mu. Later, this is going to be the Hamiltonian of an adiabatic quantum computation, and what we will see is that the ground state in particular is an eigenvector, so it will also grow orthogonal, it will become orthogonal to such a vector v. So eigenvector, any eigenvector other than v becomes orthogonal to v in the limit for large mu. So now let's apply these three mathematical tools to adiabatic quantum computation. So the three tools were, first of all, we have now exact expressions for the eigenvalues and the eigenvectors. we have, as a function of mu, we have relationships between the size of the gap and the amount to which eigenvalues swap the eigenvectors as a function of the size of the gap of the narrowly avoided level crossing. And finally, the fact that as mu goes to infinity, we have that all the eigenvectors become orthogonal to V. All right, so now after the math, let's get into the physics. Quantum computing can be done in many different ways. As far as the hardware is concerned, there's superconducting circuits, trapped ions, atom computing, photonics, and so on. But perhaps more importantly, there's different software we can run on them, in the sense, or operating systems, if you like, in the sense that we can pursue quantum computing algorithmically. That's the most popular method with quantum circuits. Or we can use the adiabatic method of quantum computing, which is what I will focus on here. There's also measurement-based quantum computing, which is popular in quantum optics-based quantum computing. And then there's also the relatively new and very difficult topological quantum computing. What's important to know here is that these different ways are quite different but equivalent, in the sense that they are of equal complexity up to only polynomial overhead, which means whatever can be done efficiently with one of those methods can also be done efficiently with the other methods. So this means that whichever one of these operating systems we choose, whatever we find out about the relationship between mathematical difficulty and physical hardness, whatever you find out actually applies to any way you do it, because the methods are equivalent. Whatever we find out, we can translate, in fact, explicitly, concretely translate into the other paradigm. So I will focus here on adiabatic quantum computing, so AQC. And the reason is that adiabatic quantum computing seems to offer a clearer physical intuition into how and why mathematical difficulty translates into physical slowness of the execution of the calculation. How does mathematical hardness translate into physical slowness? Yes, so our recent work that I want to talk about is that computational hardness translates into physical slowness. And the key in this, the key insight here is that to understand that link between the math and the physics here, entanglement, the dynamics of entanglement is the key. And that finding is kind of universal because the various ways that you can do quantum computing are equivalent up to only polynomial overhead. So what is adiabatic quantum computing? A little bit on the background of it. The background is a two-step approach to solving mathematical problems, or computational problems. First step is formulate the computational problem, or reformulate it as finding the minimum of an energy function, or a cost function. And then secondly, design a physical system, classical or quantum, with that energy landscape. And then, if you can do this, the challenge to find the solution to the problem becomes the challenge to get the system into the ground state, into the lowest energy state. If you have the lowest energy state, you can read off from it what the solution is to the mathematical problem. So for example, combinatorial optimization. Let's say we consider the traveling salesperson problem. So you have to travel to various cities and you want to do that in the most efficient way, the shortest route. Very difficult to do this, to find the optimal route. Or you are in charge of scheduling classes at university. So you have to assign classrooms and times to various classes, keeping in mind tons of constraints that all students need to be able to take their classes, so they cannot clash. Two different classes that some students have to take cannot be at the same time. And so it's very complicated. It's a combinatorial optimization. In the case of the traveling salesperson or scheduling classes problem, you can, in the traveling salesperson problem, the cost function could be simply the length of the path. So you create a physical system such that the longer the path, the higher the energy. So clearly, the lowest energy path, the lowest energy state of your system is then the solution, the shortest path. Or scheduling classes. So again, you describe which class happens in which classroom at what time. All of this can be written down in binary, of course. You know, the number of the room and the time of the classes and which subject is being taught by whom. All of this can be done in binary at the end of the day. And what you want, therefore, is a long binary string that tells you this class at that time in this room and so on. And the energy functional is simply such that as long as you're not violating any constraints, energy is zero, but as soon as you violate a constraint, you pile on energy. And therefore, also with the scheduling of classes, it's all about minimizing the energy. This principle is super general, by the way. Even factoring integers can be reframed as finding the minimum of an energy cost function. Okay, so we translate the computational problem at hand into the problem of finding the lowest energy of some physical system. And it's Hamiltonian, we call the problem Hamiltonian, HP. The ground state then of HP encodes the solution. In binary, right? So it's ones and zeros so that we can do it with qubits. This is extremely general. It includes, for example, factoring. And it's really, really hard to find any kind of computational challenge that cannot be written in this way. Now, one might think, oh, that's good, but I don't need a quantum computer for this. I can do this on a classical computer. I have an energy landscape, and I just need to find the minimum of it. Shouldn't I be able to do gradient descent? And gradient descent is very powerful. We know that from machine learning. It's based on using essentially gradient descent. But it is unfortunately inefficient if the problem at hand is really hard. Namely, if the energy landscape is rugged. Imagine that the energy landscape is some landscape with lots of valleys and high mountains and a lot of local minima. So if you do gradient descent and there are lots of local minima and these local minima are far apart from each other, that's the worst case because you're probably going down into a local minimum and stuck there. And then you have to find out, oh yeah, well, maybe I should climb out of this, but then where? It's a long distance to the next local minimum to fall into, and that's just a nightmare to do. So then one might think, okay, let's do it with the physical system, and we just take the physical system and we cool it down. At zero temperature, shouldn't it be in the ground state? Or if the system still gets stuck in a local minimum, then maybe we can use quantum tunneling and the system will tunnel out of that local minimum, eventually find its way to the global minimum. Tunneling could help, but I would argue it's useless. It has no role in adiabatic quantum computing because it's useless. Tunneling is exponentially suppressed with the distance that you need to tunnel. So it's just not an efficient way of doing things. So what we need is a better way to find a minimum of Hamiltonians in a physical system. A better way to leverage quantum mechanics. Now let's remember what makes quantum computers powerful in the usual algorithmic paradigm, where we have quantum circuits and quantum algorithms. Well, the conventional algorithmic quantum circuits kind of quantum computing is powerful because of entanglement. We know that we need a lot of entanglement. We need to get deep into the Hilbert space to perform a calculation that cannot be classically simulated. In order to actually get something powerful, we need tons of entanglement. And I'm claiming that it's the same with adiabatic quantum computation. It's not really a surprise that it's not tunneling, it's entanglement that makes adiabatic quantum computation powerful. Entanglement is the key resource that allows the system to find the true ground state efficiently. So let's see how adiabatic quantum computation is systematically using entanglement. So let's remember how the adiabatic protocol proceeds. First, we initialize the system. We prepare our qubits, which encode the ones and zeros, of course. We initialize our qubits in the ground state of a simple known Hamiltonian that we have under control, such as this initial Hamiltonian, sigma x's, and the ground state is the tensor product of plus states. This is an unentangled state because it's just the tensor product of these plus states. But the plus states are equal linear combinations of zeros and ones. And you have a tensor product of all of them, which means you can view this initial state also as an unbiased equal linear combination of all possible ones and zero states. All possible computational basis states. Just because we don't know what the solution is, so we just assume as a starting state a state that is having all candidate solutions in equal measure. One can do better than that, but if we don't know anything about the problem at hand, this is a safe way to go. Okay, so that's the initial state. It's an equal linear combination of all bit strings, written as computational basis states. Computational states, basis states being the ones where you have the qubits either in a zero or in a one state. So then the adiabatic computation proceeds in this way. In the simplest case, we have a Hamiltonian that depends on time. And initially, for t equal to 0, it's just the initial Hamiltonian. And then as little t approaches capital T, that term vanishes, and we have just the problem Hamiltonian. So we're slowly, that's the point, slowly changing the Hamiltonian from the initial Hamiltonian with this ground state. We prepare the system in that ground state. We change the system adiabatically, slowly, so that eventually it becomes a system with just a problem Hamiltonian. And if we do this indeed slowly enough, then the ground state evolves into ground state, evolves into ground state, and at the end of the evolution, the system is the ground state of the problem Hamiltonian, and that is the solution to the computation. So for that we need the adiabatic theorem. And the adiabatic theorem states that if the evolution is slow enough, the system remains in the instantaneous ground state throughout. I mean, not exactly, but with super high accuracy. Now, what is slow enough? Slow enough depends on the minimum energy gap that exists during the evolution between the ground state and the first excited state. That's the minimum energy gap between ground state and first excited state. And then it's known that the runtime scales like 1 over the gap squared. So the smaller the gap, the slower we have to evolve. The slower we have to go in the adiabatic quantum computation in order not to lose the ground state. The system should stay in the ground state because we do want the really lowest energy solution. If we don't care whether we are actually in the really lowest energy solution, we can go a little faster. But if we're really going for the solution, the unique lowest energy state, then we need to abide by that constraint. So as is well known, a small gap forces a slow computation. So clearly what we anticipate here is, and that's well known, that the hardness of a mathematical or computational problem will translate somehow into the smallness of the gap. So the ground state's eigenvalue is changing over time. The first excited state's eigenvalue is changing over time during the adiabatic evolution. They never cross, but they can get close. And the closest they get determines the speed with which we can do our computation. So let's put this all together using the mathematical tools that I talked about at the beginning. So let's connect the hardness of a computational problem to the usage of the resource of entanglement in adiabatic quantum computation. So we start having a problem Hamiltonian HP. We start with a simple Hamiltonian, and the system is prepared in its ground state, for example, a uniform linear superposition, as we just discussed, of all computational basis states, all strings of ones and zeros. And then we want to evolve to the ground state of the problem Hamiltonian, the solution. So the claim is, or the question I want to address now is this: how does a hard computational problem, and remember what that means, a hard computational problem is a problem whose energy landscape is highly rugged. It has lots of mountains and valleys and local minima, lots and lots of local minima that are at a large distance from another. Now, what does it mean that two local minima are at a large distance? In what sense is this distance defined? It's the Hamming distance. And that's the natural distance here. How many bits do you have to flip to get from the computational basis state that is this local minimum to the computational basis states that's that local minimum? You have to flip a certain number of bits, and the more bits you have to flip, the larger is the distance, Hamming distance. So the question is, how does a computationally hard problem, a problem whose energy landscape has lots of local minima with large Hamming distance among them, how does that enforce that the ground state during its adiabatic evolution has to become entangled, and even highly entangled? It does, and I'll show you now why. Remember that the ground state initially is not entangled at all. It's just a product state of these plus states. Right? So it's not entangled at all. But I want to show you now that there's an easy way to see that the computational hardness, the ruggedness of a computational problem directly translates into the ground state having to accumulate a huge amount of entanglement. Now, in order to see this, we need to remember now a result that I told you about at the very beginning in the pure math part, before I even started with the physics. And that result was the tool number 3. And I'll now show you that it implies, you can see that the evolving ground state during adiabatic quantum computation sequentially sheds its components in the direction of computational basis states that are of high energy. So the ground state as it evolves initially consists of an equilinear combination of all possible candidates for solutions, all bit strings of ones and zeros. But some of them are really bad guesses because their energy is very high. Some of them have low energy. And as I will show now, those of high energy will quickly drop out of the composition of the ground state. Ground state initially contains all computational basis states, but it will shed those of high energy, the highest energies first, then those of the medium energies, then those of the low energies, so that eventually it settles on the ground state. It gets rid of everything else sequentially. So the adiabatically evolving ground state first becomes orthogonal to the computational basis state with the highest energy. That's the most forbidden, or is like in the traveling salesperson problem. It would be the longest path you could take. Those I get gotten rid of quickly. or when it comes to scheduling classes at university, those schedule candidates that have lots of violations of constraints, they would be shed very quickly. And then, of course, the ground state gets rid of all the lower energy candidate solutions until eventually it just becomes composed of just the low energy candidates for the solution. So to see why that is so, let us remember the tool number 3 that I told you at the beginning. It's just a pure mathy thing. So we have a Hamiltonian, and we add to it mu times the projector. Then as mu goes to infinity, remember, this part dominates over that, and V becomes an eigenvector to the total Hamiltonian. Which also means, and that's what's important here, this also means that the other eigenvectors of the total Hamiltonian become orthogonal to V. As V becomes one of the eigenvectors, all the other eigenvectors have to be orthogonal to it. Now, but where does that situation occur in adiabatic quantum computation? All the time. All the time it occurs. And that's because we can take our problem Hamiltonian, which we add to the original initial Hamiltonian. We can decompose our problem Hamiltonian into a sum of projectors, with prefactors being the energy eigenvectors. And instead of adding the Hamiltonian, the problem Hamiltonian all at once, we can, as a Gedanken experiment, also add one projector at a time, which is this process here. In fact, we don't have to do this manually. Nature does it for us, because those with the highest energy eigenvalues will dominate first, and then those with the lower energy eigenvalues will dominate later. So effectively, by doing an adiabatic quantum computation, where we add the HP to the initial Hamiltonian, usually we schedule it in such a way that the initial Hamiltonian gets a prefactor that goes to 0, and this one gets a prefactor that goes to 1, but it's completely equivalent to just rescale the whole thing so that the original Hamiltonian stays and the problem Hamiltonian goes to infinity. I mean, the prefactor goes to infinity. And then what we have is that this situation occurs for every one of the computational basis states, and this mu is multiplied with the energy eigenvalue there. And so what we see is that one by one, during an adiabatic quantum computation, these computational basis states, starting with the ones of the largest energy eigenvalue, the most forbidden ones, go through that phenomenon where they dominate the total Hamiltonian. This eigenvector becomes one of the eigenvectors of the total Hamiltonian. All the other eigenvectors become orthogonal to this one, including the ground state. So the ground state is shedding its components in the direction of these computational basis states, one by one, starting with the ones of the highest energy. Yeah, I already said all of that. Okay. So, what we saw is that the ground state sheds its components in the direction of computational basis states, and therefore potential solutions that are highest energy first and then the lowest energy, and in this way it eventually approaches the ground state of the computational Hamiltonian, the problem Hamiltonian. So now, let's remember what is a computationally hard problem. I think I've said it a few times by now, but just to drive home the point, it's the case where we have many local minima in the energy landscape, and these minima are far apart in Hamming distance. That's the worst case. That just makes it hard. Now, the ground state's adiabatic evolution during adiabatic quantum computation confines the ground state eventually, after it has shed all the high energy candidates for the solution, it becomes confined to the subspace spanned by just the low energy local minimum. And that's when it gets critical, right? At high energies, getting rid of the highest energy, clearly wrong solutions was easy. But now we get into the critical phase, where the ground state is a linear combination of only those computational basis states that are the local minima or close to the local minima that are far apart in Hamming distance. So the ground state must, in the case of a computationally hard problem, it must become eventually, during its evolution, as it has shedded the highest and the medium energy candidate solution, it must become a superposition of computational basis states that have a large Hamming distance from each other. So the ground state, during the evolution, must go through a phase where it is a linear combination of computational basis states of large Hamming distance. So you have to flip a lot of bits to get from this one to that one, right? Because, by assumption, it's a hard problem. Minima, lots of minima means lots of terms, and then large Hamming distance means that a lot of bits have to be flipped from here to there, and so on. But you see, such a state, which is a linear combination of computational basis states, which have a lot of bit flips in between them, is hard to factorize. It doesn't factorize. In other words, it is, by definition, highly entangled. It has a high amount of multi-part entanglement because they don't agree on bits. Because if this state and that state were to agree on like 27 bits, sure, then you can factor out these 27 bits and the rest becomes a sum. But the less they agree on bits, the less you can factor, the more you have multi-part entanglement. So such a state doesn't factorize well. It must be full of entanglement of all sorts of degree of multi-part entanglement. So the ground state, even though it is initially an unentangled state, and also when the final state, the solution to the combinatorial optimization problem, I mean, we're just focusing on combinatorial optimization because it's intuitive, that ground state is usually unique. Like the shortest traveling statesperson path. It's usually unique, which means that the ground state, after everything is said and done, the ground state of the computational Hamiltonian, of the problem Hamiltonian, is just a computational basis state, and as such, a product state. It has no entanglement. What we just saw is that in adiabatic quantum computation, the system starts unentangled and ends unentangled, and in the middle it goes through this. A huge amount of high multi-partite entanglement, directly related to how hard the problem is. How many local minima, how far apart are they? So for example, imagine that we have two states of maximum Hamming distance, which would be a GHZ state. It cannot be factorized into anything. It's a high multi-partite entangled state. So the life cycle of entanglement during an adiabatic quantum computation starts with a product state, usually, the linear combination of all computational basis states, equal to linear combination, is actually product state because it can be written as a tensor product of just plus states, and that's unentangled. And then the final state, if there's a unique solution, it's just a computational basis state, also unentangled. But we saw that for hard problems, hard computational problems, the adiabatic evolution must first create and then destroy a huge amount of entanglement, because it has to go from unentangled to unentangled while going through this huge amount of entanglement. Okay, so adiabatic quantum computation of a computational hard problem involves the generating and destruction of a huge amount of entanglement. There's a mountain of entanglement that needs to be created and then annihilated again. How is this entanglement created and destroyed? Well, remember the mathematical tool number 2 that I told you about before we went into the physics. I just started with 3 slides of pure math. Remember, as a Hamiltonian, a parameterized Hamiltonian evolves, its eigenvalues evolve, but generically, in the absence of some symmetry, they will never cross. But if they get really close, then they swap their eigenvectors. And it is exactly this swapping of eigenvectors that changes the entanglement. During the adiabatic evolution, the entanglement of the ground state, or any other state, doesn't change because the state doesn't change until you are at a narrowly avoided level crossing, where it does change, and it can change pretty suddenly, namely as you go through the narrowly avoided crossing. So it is precisely at the swapping of the eigenvectors at narrowly avoided level crossings that entanglement is either generated or destroyed. Now, remember that there was this result that if the level crossing is narrowly avoided, then we have almost perfect swapping of eigenvectors to the eigenvalues, and therefore a huge amount of change in the state, and therefore a potentially huge amount of changing the entanglement, and increasing or decreasing entanglement. You weave or unweave the entanglement in this process. But if the level crossing is not so narrowly avoided, but with a wider gap, then this is much less perfect, much less entanglement can be created, much less entanglement can be destroyed in a widely avoided level crossing. So to efficiently create highly entangled states fast, quickly during the evolution, you have to go through narrowly avoided level crossings. That's the most efficient way of generating entanglement. But narrowly avoided crossings, level crossing, means small energy gaps. And small energy gaps means you have to go slow, because otherwise you risk that the system gets excited up from the ground state, and then you don't find the final ground state anymore, you don't get the solution. So what we see here is the underlying mechanism under the hood that relates the computational hardness to the physical slowness of the calculation. So the hardness of a computational problem, in the sense of how many local minima, how many false minima it has, and how far they are apart from each other in Hamming distance, translates, as we saw, directly into the amount of multipartite entanglement that must be created and destroyed during the adiabatic quantum computation. And then we saw that the entanglement creation and destruction can only happen at the avoided level crossings, where the eigenvalues swap, at least partially, sometimes almost completely, swap their eigenvectors. And we saw that small gaps are more efficient at creating entanglement. So if a lot of entanglement needs to be created because the problem requires it, in fact the problem enforces it, right? There's no other way to go through the adiabatic quantum computation than going through that stage where the ground state is the super highly entangled state. So we must have small gaps. Otherwise we can't create that much of entanglement, and therefore that's why it has to be slow. I just noticed that the word tunneling doesn't come out, because it has nothing to do with it. Tunneling is when you leave the system alone and it flows apart. We don't. We force it adiabatic and so on. Okay, so, and then the small gaps, of course, translate, as is well known, into slowness of the calculation. So a hard problem is a problem with a rugged landscape with distant minima. The ground state must therefore temporarily, during the adiabatic evolution, become a superposition of Hamming distant states, and Hamming distant states, a linear combination, if the ground state is a linear combination of Hamming far apart states, then the ground state has to be temporarily highly entangled. The creation and destruction of this entanglement requires sharp eigenvector swaps at avoided crossings, but these correspond to small energy gaps, and therefore that enforces that we have to go slow. That's essentially how far we got, and so I think what we have is a better understanding of what's going on and some tools, because we can calculate these things explicitly. And what do we now want to do with it? Well, we want to predict quantum advantage. So when is it that a problem is classically hard and still quantumly doable? That's ultimately the challenge. And so what we need to study for that purpose, you see here, I kept the problem fixed. The problem size was fixed, the Hilbert space was fixed, and all of that. But of course, what's of interest from the computer science perspective is how the runtime or how the resource requirements scale as I scale up the size of the problem. Like if I go from a traveling salesperson problem of 20 cities to 200 cities, or scheduling classes, you know, more classes, then it takes longer to do it, to do the scheduling, but how does this scaling law work? And there's an observation that has been made in the literature, which I think will be relevant for this. So as I said, the key here for discovering quantum advantage situations is to examine the scaling of the minimum energy gap with the size of the problem, with the number of the qubits involved. And what is hard for adiabatic quantum computation is if the gap closes exponentially. And actually, often in the literature, they speak of the gap, the smallest gap that occurs during the adiabatic evolution. I don't think that's the right way to look at it, because what we saw here is that a huge amount of entanglement needs to be generated and destroyed. That doesn't work in one avoided level crossing. No, you need a lot of avoided level crossings, each contributing its entanglement, and so it's a collaborative effort of a lot of avoided level crossings, and so it's a lot of gaps that need to be considered. But overall, we can ask, you know, how many closed gaps do we have, so how much do we have to slow down? And what's bad news is if the gap closes exponentially fast with the number of qubits involved. That can happen, and in this case, it's hard. Even quantumly, it is hard then. And interestingly, we know a situation like that from condensed matter physics, from quantum phase transitions. Remember quantum phase transitions? These are phase transitions that have nothing to do with temperature. They happen at zero temperature. They happen when you change a parameter of the Hamiltonian, such as in adiabatic quantum computation. Everything is supposed to happen at zero temperature, and you just change this parameter that gets you from the initial Hamiltonian to the problem Hamiltonian. So if the gap closes exponentially fast with the number of qubits, that is to say with the size of the problem, then that's bad news for adiabatic quantum computation. And because it's equivalent up to polynomial overhead, it's bad for any kind of quantum computation. And we know from condensed matter physics this corresponds to first order quantum phase transition. And then let's just say first order quantum phase transitions have that property of the gap closing this way. Doesn't mean that every hard quantum computation that's not efficient translates automatically in a first order phase transition. A quantum phase transition can, but it doesn't have to. What's easy for adiabatic quantum computing, what is efficient, is if the gap closes only polynomially, and we know from condensed matter physics that there are situations where the gap closes only polynomially fast in the thermodynamic limit of having infinitely many qubits, and that's when we have a second order quantum phase transition. Of course, there are other phase transitions as well. They don't have to be first and second order. They don't have to be clean in one or the other, especially when it's not a physical problem of a crystal or spin glasses or anything, but instead if it's actually a computational problem, then all bets are off. It could be more complicated than that, just first and second order phase transition. But what I find fascinating is that the computational hardness of a mathematical problem translates bang into something that we can talk about in terms of condensed matter physics, right? And this whole connection between hardness of a computational problem requires directly that the ground state of the adiabatic quantum computation must undergo a phase of tremendously large entanglement, needs to be created and then destroyed. And then we saw that entanglement creation can only happen at avoided level crossings, can happen efficiently, and that's what you need if you need a lot of entanglement, only for narrowly avoided level crossings, and that means small gaps, and that means the slowness. So you might look at this point like, well, yeah, that's just how it is. It's a hard problem, we have to be slow. But we do know that there are quantum advantages. We do know, for example, that the algorithmic quantum computing with circuits, quantum circuits, is equivalent to adiabatic quantum computation up to polynomial overhead, which means that, for example, Shor's algorithm can actually be implemented this way, and it has a quantum advantage. So there's got to be something more to find out, namely, and that's what I'm proposing. We use these methods and find out, how does Shor look here? How does Shor create a lot of entanglement, and we can still do it without having an exponentially fast closing of the gaps? I think that if we study these things, we might be able to improve optimization problems or other things quite significantly. In general, I would advocate that we do not silo ourselves into just using one approach, like only adiabatic quantum computation or only circuits, because they're equivalent after all, and what we learn in one, we can translate into the other. And quite directly, by the Feynman-Kitaev method, for example, Shor's algorithm can be directly translated into an adiabatic quantum computation. And then adiabatic quantum computations can also be discretized, and then you get the circuits. So it's not just a theoretical construct, it's explicit constructions that show us how adiabatic and circuit quantum computing are the same. So I leave you then with the challenges, which are use the new exact tools to identify quantum advantages, and then translate the findings back and forth between the various paradigms of how to do quantum computing. Thank you very much.
Very much for the talk. Now I'd open the floor for a few questions.
Thank you.
Thank you for the insightful talk. I wanted to know your framework. You mainly consider problem Hamiltonians that have this direction property. However, there might be problems that don't have this pure Hamiltonian. So
That have what?
that don't have this exact form that they're a sum of projections. For example, cubes, you could have different Hamiltonians as well.
Well, it's just the spectral theorem. If it's a self-adjoint operator, it has a decomposition into projectors. It always does. These projectors may not have easy interpretations, but they always exist. Just because on the grounds of being self-adjoint.
Can I ask another question? So in this adiabatic quantum computing, you necessarily go through states that have high entanglement. However, if you compare this, for example, to classical simulator annealing, you don't even consider entangled states. So wouldn't that be a question to ask whether a smaller search space that you have in classical might even be more favorable than a bigger search space that you would have in the quantum regime?
Yeah, well, maybe for the not so hard problem. Right? But if you actually have a lot of local minima that are far apart, then what other methods do we have?
Yeah, sure, but we don't know whether there's maybe even more local minimas within the bigger search space which contains the entangled states. Like this is something that we cannot see a priori.
Well, if you know something about the problem at hand, for example, you know that, in this region there are local minima and the global minimum cannot be there, then yeah, of course you should build that in, and right to your choice of initial state, for example. Clever scheduling can make use of any prior knowledge that you have, and that might actually be a major gain of efficiency. I agree.
So this connection between the hardness of the problem and many local minima, how does the Hamming distance come into this hardness? Is this encoding some kind of assumption about the form of the Hamiltonian that you're minimizing?
Well, what other distance could we use? I would say if you use combinatorial optimization, where the problem is formulated classically and the solution is classical as well. In that case, the computational basis states are the candidate solutions. And in that case, this is the natural notion of distance there. Now, it is true that if you instead use adiabatic quantum computation to solve another problem, something in physical chemistry, for example, then computational basis states might not be the way to look at things, because we're not expecting the ground state to be a computational basis state. It could be a highly entangled state. Right? In that case, the intuition is a little different. So in that sense, yes, I was leaning for the purpose of the intuition on the case of combinatorial optimization.
Even with the optimization problem in this case, if somebody would say engineered a problem where the two minima were Hamming distance 2 apart, and everything else was a local minimum. Or rather, you could have two local minima that are very close to Hamming distance. It feels like you could engineer such a problem in this framework, and the distance would still be small, but the problem would be hard because you'd have to search through a very large number of bit strings. See what I'm saying?
Maybe so, but the point is that if the Hamming distance is low, then the ground state is, during its evolution, will be at the later stages when only the low energy states survive. The ground state will be a linear combination of computational basis states that differ only in few bits, which means that this state factorizes much better than if it was a linear combination of computational basis states that differ in a lot of bits. See, if they differ in all bits, it's a G and C state. It's just fully multiply entangled. If the two states differ on just a few bits, then you can factor a big chunk of the states out, and you have much less multipartite entanglement in this case.
But there's different kinds of entanglement. Right? So
yes, it's multipartite entanglement.
Is this true for all of the different types of entanglement?
Sure. I mean, the larger the Hamming distance, the less they factor out. The less you can factor the state. The less ways there are to factor the state.
Like a W state, right, where it's a superposition of basis states that are all Hamming distance 2. This is, in some sense, maximally entangled, but all of its components are minimum distance.
No, it's true. You can have multipartite entanglement that is genuine and multipartite entanglement that's sort of made out of lower partite entanglement. And I suppose all of this is encoded in the two ways in which we can have a bulge of high entanglement. Namely, we can have a lot of minima, or we can have a lot of Hamming distance between them. So we can have few states with a lot of Hamming distance, or we can have a lot of states with little or a lot of Hamming distance in between them. And it's quite conceivable that the difference between a problem that remains hard for a quantum computer and a problem that becomes easier for a quantum computer I mean, I'm assuming here that we're talking about a classically hard problem. Right? So the difference between quantum advantage and not having a quantum advantage might be in exactly the nature of that bulge of entanglement there. It might be more harmless entanglement, presumably of the lower Hamming distance kind, maybe a lot of it, but it's not that bad, it's lower apartheid entanglement. Or it could be true multi-part entanglement. For example, in the traveling salesman problem, right, we know it's super hard, and be hard because it's sort of a global thing. You can't do anything locally. And that would indicate that you have, large Hamming distance matters. And that would mean high multi-parted entanglement matters. And then other problems might be much easier, maybe in some measure the same amount of entanglement, but more harmless entanglement, where it's low apartheid and you kind of can locally solve the problem and then piece it together to a global solution.
Very interesting.
Let's just go online first before the rest of the questions here. So first question is, how do you measure the quantum entanglement while the AQC is happening, and how are we sure about the entanglement getting to the maximum value?
Whether it gets to the maximum value in some sense by some measure, well, it will achieve a maximum because we have to create it and then it will have to be destroyed again, because we start and we end with zero entanglement. But whether it is the maximum entanglement possible in that space, that's a different question. That depends on the problem at hand. And then I would not advocate to measure the entanglement actually through measurements, because obviously it would destroy the coherence. But the question of how we quantify how much entanglement we actually have is a super hard one, because we don't really have good measures for multi-parted entanglement. Now there are attempts at doing multi-parted entanglement and properly quantifying that, but this remains very difficult. There are, it's even more complicated, because there's also discord, which is where you have quantum correlations in the absence of entanglement. I wrote a paper on that showing that two-partite discord arises from tripartite entanglement when you trace over, if you have genuine tripartite entanglement and genuine bipartite entanglement, and you trace over one of the three systems. And that phenomenon probably generalizes also to multi-party entanglement. It's a whole zoo out there. If somebody could classify the multi-party entanglement structures, that would be amazing. And I imagine it would be very useful to have that, so that we can distinguish opportunities for quantum advantage from non-opportunities. It's probably in the nature of entanglement that's needed and needed to be created and destroyed.
Okay. So currently there's not a lot of intuition on which metrics could guide experimental validation.
Very hard. I mean, we for bipartite systems, we have very good measures of entanglement, at least for pure state. And you could always say, okay, if I have a multipartite system, I can divide it up into two systems in multiple ways, and then ask how much bipartite entanglement do I have there. But that's not really a satisfactory measure, because it doesn't capture genuine multipartite entanglement very well. In fact, in the paper with Aina, we are suggesting to develop a measure of multipartite entanglement based on this phenomenon. Basically, if you have a state that is highly entangled, highly multipartite entangled, then you can ask, if you want to create it through an adiabatic quantum computation, how slow does it have to be? But you see, it doesn't help us, because this is just turning things upside down, right? But if what we want is a measure of multipartite entanglement, we could ask, how hard is it to create that state through an adiabatic evolution? Let's say always starting from the same plus state, plus tensor plus state.
Thanks. And then the final question from online. It says, then the question arises, can one not from time to time apply a perturbation such that the gap becomes smaller, or in other words, we can generate a large amount of entanglement.
So we can apply what? I missed one word there.
So the question seems to be related to, can we leverage this and apply a perturbation from time to time, such that we can force this entanglement generation? At least as I understand.
Oh. Yes, I don't know, I don't immediately see where that would be applicable, but we can certainly do that. We can use this result to design algorithms that will generate custom-made entanglement structures, because we know how to do it. You just have an avoided crossing. We can calculate exactly which V you need to do what you want. But yeah, if you want to design highly entangled states by adding projectors one by one, that can be done.
Okay. Well, thank you so much. At least for the online stream, I think we'll come to a close. So thank you so much to everyone who participated with questions and who listened. And the next colloquium will be in September on the 25th, where we'll have Professor Seva Garibian on site presenting his work on dequantizing the quantum singular value transform, its hardness, and applications to quantum chemistry and the quantum PCP conjecture. So, yeah, have a good day, and we see you then.